started. I will begin. Heavenly Father, we thank you for this day. Thank you for these students. We pray you to guide our thoughts today and just help us to glorify you, Lord, what we do. In the name of our Brother Jesus. Amen. All right, so I need to talk to you guys about parametrically described curves. And so it's really a change in viewpoint. So previously, how have we done things? We either have y is equal to f of x, right? And you look at a graph, right? Right? Or you have, some equation involving x and y equals to, 0 usually. And so you look at the solution set, right? So to give you, for example, we might have previously talked about, well, here's a common example, something like this, right? Y is equal to x squared plus 1. This is the graph of what? F of x equals to x squared plus 1, right? So you know that. Or maybe we're just learning about these now. Here's the point 3, 2, right? And we might have looked at something like this guy, right? And let's see here, if these points, it's a badly drawn ellipse, but use your imagination. Let's say this point here was minus 1, 2, and this point was 4, 2. I'm sorry, 7, 2. Otherwise, it's not an ellipse. So it's the same distance from the center point to both of those, right? And then above and below, let's say it's 3, 4, and 3, 0. Ooh, that's a really bad picture. Let me make that 3, 1, and 3, if this is down 1, that's up 1, right? So 3, 3. So that would be an ellipse. What would the equation of that ellipse be? If I take a particular point, x, y there, what's the equation that it would satisfy?
X minus 3 squared over some a value.
No, he's got the right template here. And then y, what? Y minus 2 squared over something equals to 1.
Yes.
Would that be over x minus 3 over 4 squared, y minus 2 over 1 squared?
Right. So Josh has played with the homework in this section long enough to have a sense about it, right? But that's how you know. That's why he knew that, right?
Yeah.
There wasn't some really awesome high school teacher that taught you it in a song or something. Oh, you taught yourself your homeschool, okay. Hey, me too. Let's see here, x and y, which explains all my social awkwardness, right? Let's see here. So,
You were homeschooled?
yeah. That's why I can't talk to people, and I'm afraid of being in social situations, generally speaking. Sorry. The stuff people say against homeschooling, it just cracks me up. I'm sorry. But anyway, neither of these are our viewpoint. As we talk about curves being parametrically described, we introduce a parameter t, all right, independent of x and y. And this parameter t traces out the curve that we're interested in, right? So you could think of t as perhaps being time, but the parametric viewpoint says no, it's a little bit different. I mean, parametric viewpoint says if you want to describe a curve, then you look for f of t, let's say, and g of t, such that x equals to f of t, and y is equal to g of t, as, say t naught less than or equal to t less than or equal to t1, describes the curve. Now, the curve here, C, would be explicitly the set of points f of t, comma, g of t, such that, t naught less than or equal to t less than or equal to t1. Now, I'm assuming, just to get us started, that the domain of the parameter has to be some closed interval, but that, of course, is not actually the case. I mean, we actually can let the parameter range over all time. You could even do weird stuff like let it range over time 1 to time 7, and then also times 300 to 302. I mean, you could do that. Be weird. There might be good reasons to do that. Maybe you're parameterizing, the profit of a business, and the business is only open 2 days a year or something. So it would make sense for the time only to include the 2 days of business that is open, right? I mean, you can imagine things. But this viewpoint is very robust, and first of all, the graphical viewpoint is by far the most limited one, just graph of a function, because it has to pass the vertical line test, otherwise it's not the graph of a function, right? Now, you start looking at solution sets to an equation, well, that's not as restrictive. You can do lots and lots of things there. We've seen a lot of them in 10.1 already, right? Hyperbolas, ellipses, and those don't have to pass vertical line test, right? Those don't have to be the graph of a function. So, but this is, a curve, the parameterization of a curve. All right, well, so how do you graph the parameterization of a curve then? And how do we understand their calculus, right? Now, I think parameterized curve gets really old really fast, right? That's a lot of talking. There's a standard term for this, and I'll try to start using this for you guys, which is path. A parameterized curve is a path. Okay. Let's just start out with an example. Suppose I have x is equal to t, right? And y is equal to cosine t. And we're going to let the time, the parameter, range from 0 less than or equal to t less than or equal to, let's go all the way to 2 pi. All right? Let's try to graph this thing. So the way to do this, sort of the most rudimentary way to do, is just make a table. You put t here, you put x here, you put y here. Pay close attention to this. This is probably the last time I'll do this in here. Because I, generally speaking, try to avoid this and look for other sort of sneakier ways. But we should always be willing, able, ready to fall back on this basic method. And also, I would encourage you to think hard about maybe using technology in place of tables, right? But let's sort through it. It's a good starting point. We start at 0, right? Time 0. I plug in time 0 into x, what do I get? I get 0, right? What's cosine of 0? Cosine of 0 is 1. Now I get to pi over 2. What do I got? T equals pi over 2. X is pi over 2. Okay. What's cosine? 0, right? Feeling guilty about not doing pi over 4. I'm going to throw that in now. That's bad. Not the best organization, but here it is. Pi over 4. What's cosine of pi over 4? Yeah, 1 over root 2. I'll take that. Now, it's going to be helpful for me to put a decimal in here, 1.707. I mean, if you're doing a table of values, you probably want decimals because you're thinking about making kind of a crude sketch from this, right? Connect the dot style. Pi over 2, let's see what's next. Maybe I'll jump ahead to 3 pi over 4. So 3 pi over 4. Curses. I really need to, what is pi over 2 in terms of pi over 2 is about 1.57, yeah? Pi over 4 is about what? 0.78-ish, something like that. 3 pi over 4, what's that? It's about 9 divided by 4. It's about 2.3-ish, something like that. Roughly, very roughly. What's the cosine of 3 pi over 4? Is that right? Yeah, that's right. All right, then we get to pi. What happens to pi? Well, we got 3.14-ish for the x, and how about cosine? We got -1, right? All right, I'm running out of board space, so I'm going to jump ahead a little bit. Actually, you know what I'm going to do? This is, again, a freedom only available to me. There we go. Okay. Now we're done. We've got, it's not the greatest, but it'll do. Let's see here. So we're starting at where? Now I like to, when I'm doing this sort of thing, to be all neat and orderly, I try to do things like, I don't know, I'm going to call this B, C, D, E, right? So like point A is where x equal to 0, y equals to 1. So there's A. And then I've got x equals to 1.57, y equals to 0. Oh, I'm sorry, I've got B, which was what? X equal to, so it's about, B is somewhere in here, right? It's in here somewhere. Obviously, graph paper would be great, you know, be helpful. Let's see here, then C would be what? 1.57 and 0, so it's down here somewhere, right? It's a little bit farther than that, here somewhere. And then D, where's D? 2.3. Let's look over here, and so it's roughly speaking down here, that's where D is. And then where was, then we get all the way to 3 pi. There's like one more. And that's down at -1, right? So that's down here somewhere. So you can, I mean, it's not the greatest, but you can kind of see what's going on here. You get some sense of what the curve looks like, right, by just plugging in points. But what's the downside of doing this by hand? First of all, that's not a great picture, right? It's a very crude sense of what the curve is. It does tell you some things, right? You get a sense that you're starting up in quadrant 1. And usually we draw an arrow on this to indicate the direction of the path, like that, all right? So great. Example 2. Let's try to plot x equals to 2 plus 2 cosine t. Y is equal to -3 plus 2 sine t for 0 less than or equal to t less than or equal to pi. Now I'm going to abandon my tabular method and advocate a knowledge-based argument. the knowledge I'm going to use is from section 10.1. See, 10.1 taught me that that is the well, I don't know if 10.1 taught me or not, but the one thing we did yesterday was to notice things like that. That's going to be a parameterization of a circle, or perhaps an ellipse. But if you solve this, I think it's a circle. You notice what we got is we've got x minus 2 over 2 is cosine t, right? And y plus 3 divided by 2 is sine t. So what I'm going to do is I'm going to eliminate the parameter, all right? And if I eliminate the parameter, then that will just give me an equation involving x and y, right? If I can do that, and if it's something I already know by our previous methods how to graph, I don't need to make this table of values, right? Although I got to be careful that the range of the parameter will still inform me something, all right? So let's think through it. Of course, you see what we have is cosine squared plus sine squared is what? It's something without time, right? This is the timeless equation. Cosine squared plus sine squared is 1. So you see, squaring these two things and adding them together is going to give me 1. And I feel better about this if I rewrite it as x minus 2 quantity squared plus y plus 3 quantity squared equals to 4, which of course is 2 squared. To me, that's nice, because at this point, I can recognize that this is a circle, right? Radius what? 2, centered where? Yeah, I heard a 2 comma minus 3, I'll take that. Now, if that's all that was given, if the boxed equation that was all that was given, then that'd be the full circle, right? But that's not this. This we're given, fine print, we're given a parameterization of the circle, right? And so that parameterization says that if you look at that circle at 2 minus 3, here, right? I'll draw it dotted. I'll try to draw it dotted. So the dotted, badly drawn dotted circle here, that would be the complete solution set to the boxed equation, right? All of those points are solutions to that equation. But the parameterization, what part of this circle does it hit? And where does it go to and from? Where does it start? What's its starting point? Let's think about t equals to 0. Where's t equals 0? We get x equals to 2 plus 2 cosine 0, right? That's 4. Where does it end? What's y there, though? Y equals what? Minus 3 plus 2 sine of 0, which is minus 3. So it starts at 4 comma minus 3, right? That's its initial point. Its initial point is 4 comma minus 3, which is this guy. Where's its ending point? What happens when you plug in pi? X of pi, 2 plus 2 cosine pi, also known as 0. Y of pi is minus 3 plus 2 sine of pi, also known as minus 3. So its ending point is right here, right? I suppose you still got two possibilities, right? It could be the lower half or it could be the upper half of that circle, given that that's the starting and ending point. How could you be sure about which one it is? Yeah, plug in pi over 2. Sounds like a good option. So if we plug in pi over 2, what happens? Sorry, I'm kind of peppering everything around. You know, if I was writing this out on a piece of paper, I would like do these in order, right? I'm sorry, I end up adding stuff not where I want to put it in principle. So x of pi over 2 is what? 2 plus 2 cosine pi over 2. Y is minus 3 plus 2 times the sine of pi over 2, which is what? That's 2 and minus 1. So pi over 2 gives me the point 2 comma minus 1, which is this guy. So apparently it's the upper half, right? So the curve is in fact this guy. There's a plot of that path. Now, and you can almost, you can geometrically understand what's going on here. Basically what's going on is we're looking at this half circle, right? And we're just thinking about, you can explain what t is geometrically. T is the standard angle measured, well, it's not the standard angle, right? It's the very non-standard angle measured from the pole at 2 comma minus 3 around this circle like that, right? And we're going from t equals to 0 here to t equals to pi over there. Now that you see that, if I was to ask you to parameterize something else, like what if I asked you to parameterize just this piece down here and say in that direction, where this angle is pi over 3. How would you parameterize that little arc of the circle? Switch the domain, right? So you just you'd force t to range over so that is what? That is minus pi over 2, if you like. What do you guys want to look at? You want to look at that as minus pi over 2? You want to look at it 3 pi over 2? Let's look at it 3 pi over 2, right? So you got 3 pi over 2 minus something less than or equal to t, less than or equal to 3 pi over 2 plus something, What's that something? Well, by symmetry, pi over 6, right? So I do 3 pi over 2 minus pi over 6, 3 pi over 2 plus pi over 6, and that would allow me to select just that part of the circle. What if I wanted to make the circle have a clockwise parameterization instead of counterclockwise? This is a counterclockwise. Counterclockwise. CCW, counterclockwise. There are these things called clocks. They have hands on them. You see them on walls in any building except for this one. But if you want to change from counterclockwise to clockwise, what you do is replace t with minus t. That's one way to do it. If you just swap out t for minus t, it makes the angle go the opposite way. So would a table of values been the right way to go for example 2? I argue no. I think understanding section 10.1 and applying that knowledge is a far superior method, right? So as we think about paths, if we think about parameterized curves, there's a couple of sort of standard tasks we have to face. The one is to plot them by some method. The other is to find their corresponding Cartesian equation, right? So let's just sort of make a definition. Goodness gracious. If, and I need some notation here. So let's say r of t, r vector of t, equals to x of t comma y of t, gives a path for, say, t naught less than or equal to t less than or equal to t1, then if we set x equals to x of t and y is equal to y of t, and eliminate t somehow, then the resulting equation in x and y is the, goodness gracious, Cartesian form. What on earth is going on? Of the path. I'm not very happy about this terminology. Now, you notice that I'm using x of t and x. So this, I introduced, so here I'm suggesting that a lot of times we'll write x of t here instead of g of t, or f. I mean, sometimes we overuse x and write x of t here and y of t. You know, but to be fair, there's two other functions, f and g, and those are given to describe the curve. So this right here is vector notation. You'll see this, especially in Physics 231. This is actually the position. It's the position of the particle at time t. You need a pair of functions of time, one for x and one for y, that describes the position of a particle at time t. And that is what we're thinking about here, actually. Now, the other way around is finding a parameterization, right? The vice versa of this is if you're given, right, given C as solution set of some equation which we can write as f, big F of x comma y equals to 0. So this equation defines C, a curve, right? Then what does it mean to parameterize C? There also might be some inequalities attached, like we assume that x range is positive or y is negative or some other such thing, or maybe we're looking for the part of the curve that's between x equals 0 and the line y equals x in the first quadrant. I mean, you can add conditions to the f of x, y equals 0. But generically speaking, this describes tons of curves. Like this could be x squared plus y squared equals to 0, well, x squared plus y squared minus 1 equal to 0. It could be x squared minus y squared plus 1 equal to 0. I mean, it could be circles, it could be hyperbolas, it could be lines, it could be parabolas, it could be all kinds of stuff we don't have names for. Just a generic equation. Combine x and y in some convoluted fashion, set it equal to 0. This is an equation in x and y. The locus, the collection of x and y that solve that, is a curve, all right, generically speaking, usually. A parameterization of that curve is what? A parameterization of C is a pair of functions, say x of t and y of t, such that f of x of t comma y of t is equal to 0. In other words, it's a pair of functions that when you plug it in to the defining equation for the curve, it works. This is what I did last class to find the parameterization of the circle and the hyperbola that we looked at. All right? So let's find parameterizations of my first two examples. The things I drew on the board here, let's find parameterizations of those. Example 3 here. So we could do this. Parameterize. Sometimes you don't have to make it complicated. We could use x equals to t. Sometimes you can use one of the Cartesian variables as the parameter. That's a choice that you can sometimes make and sometimes helpful. If you do that, then we put y equal to t squared plus 1. This right here, for t in the reals, this is a good parameterization of that hyperbola. Excuse me, parabola. What direction does it go? As t increases, which way do we go on the curve? Left to right or right to left? Right. I mean, correct. See here, like this, right? For example, this is t equals to 0, right? And this point over here would be t equals to 1. What's the parameterization of this one? How about this? I put x equals to 3 plus 2 cosine t. Y is equal to 2 plus sine t. And if we want to, suppose we just want to cover the ellipse one time, then we can do 0 less than or equal to t less than or equal to 2 pi. There you go. That is a parameterization of this ellipse. Because if you plug this in, what happens? X minus 3 gives you 2 cosine t, right? Let me work it out. So x minus 3 squared over 4 squared plus y minus 2 squared over 1, well, 1 squared, dumb. But this gives me what? This gives me 2 cosine t quantity squared over 4. 4 squared. Wait a second. Oh, yeah, this isn't going to work. See, good, we found a mistake. What happens here? I get 2 squared cosine squared, right? Now the y minus 2 is fine because y minus 2 gives me what? That gives me a sine squared t, right? Because the 2's cancel. When I plug this up in here, I get y minus 2 is sine t. So that's going to give me sine squared. But the other one in its current form is going to give me cosine squared over 4. That's a 4 squared, right? So I need to do something to fix that. And I think Josh was right about there being a 4 in the equation because this is distance 4. I think he's right. That's supposed to be 4 squared there. So how do I mean, what's wrong here in my parameterization? My parameterization is not working. We're seeing that. We didn't get back 1. Yes, precisely. We're supposed to change that 2 cosine t to a 4 cosine t. With that modification, when we plug it in, we get a 4 squared above and below. They cancel, and we get sine squared plus cosine squared is 1. So to parameterize an ellipse, we use sine and cosine appropriately shifted like this. What if I wanted just this part of it? I'm trying to, sorry. And I want it, to be, I'll keep it simple here, counterclockwise oriented. So, instead of doing this, what should I do instead? Cross that out, instead do what? That's a good way to think about it. Sure. We want 3 is equal to 3 plus 4 cosine t, and we want 3 is equal to 2 plus sine t for our t naught, right? What does that tell me? This tells me that I need cosine of my initial time to be 0. And I need sine of my initial time to be what? Looks like 1. So what t naught does that for me? Yes, pi over 2. Then geometrically, you should kind of pick up what's going here. This is pi over 2, right? So really, you could visualize t as being the angle swept like that. Right? So the one that gets us down here is going to be 3 pi over 2. But you could also derive that from solving, 3 equal, you could, to get the other point, let me use some color coding here. We could also set this equals to 3 and this equal to 1, right? Which would mean that I need cosine to be 0 again, but I would need sine to be minus 1. And that happens at 3 pi over 2. Of course, it also happens at lots of other points, but geometrically, these are the ones that we want because there's a sort of a continuous sweep from here to here like that. Yeah. All right. Sometimes problems don't have any particular, this was example 4. Sometimes problems don't have any particular anchor to anything. I mean, you can talk about things without regard to graph. You could say, well, x is equal to t plus t squared, and y is equal to t minus t squared, and then you can say find the Cartesian form of the given path. Now, here's what your book would say. It would say the rectangular form, or rectangular equation. I object. It's Cartesian. Equations involving x and y are Cartesian equations. If they involve t, then they're parametric equations, all right? T is not sacrosanct. I mean, you could use lambda or theta or something else for t, but I'll try to keep with the t just so you don't go nuts. You notice, by the way, guys, t has a completely separate geometric meaning in this problem versus that problem. On this board here already, even example 1, we have 4 completely geometrically distinct meanings for time t, right? So like one of the questions students tend to ask in this part of the course is like, well, what's t? What's t? Because you know what x and y is, right? So invariably, you guys will ask me, like, what's t? Well, what's the problem is the question. I mean, t has a different meaning in different problems. It's attached to the curve we're talking about. One good answer to that is if you have a curve, a lot of times, the curve looks like this, whatever. Well, if this is where t is equal to 0, you can think about t as being the parameter. You can think about t as being the parameter along the curve. So it's essentially a coordinate system that bends with the curve and goes with it. Right? So t is something like that a lot of times. Of course, you can do perverse things like have the time, you can have a curve that goes, you have a path that goes like this, right? But then it goes back, but then it goes back, but then it goes back, and you could like go back and forth. And there it gets harder to describe exactly what t is, but roughly speaking, it's kind of just a coordinate along the curve is a good intuitive version. Here, I wouldn't advocate doing anything except for algebra. Basically, we want to play a game where we eliminate t, right? So what I would do is I would add equations. If I add those 2 equations, I get x plus y equals to what? What's that? 2t, all right. If I subtract them, what do I get? Yeah. Not saying I need to. Maybe I should just use the first one, though. What's the first one tell me? It tells me t is equal to x plus y over 2. That's actually pretty much all I need to eliminate t. Then I just go back up, pick whichever one of them you like. Let's say the second one. And we get y is equal to what? Y is equal to t, which is x plus y over 2, right? Minus parentheses x plus y over 2 quantity squared. There you go. That is a Cartesian form, the solution set to that equation will give me the path. Now, it may or may not be possible to actually, find. I mean, it may or may not be possible to realize what's boxed as a graph, right? I think this one. I'm sorry. I think this is one we talked about earlier. Is it exactly it?
Yeah.
It's.
I think it's t squared plus t over t squared
Oh,
minus t.
so it's almost it's
Pretty much.
kind of the same thing, but let's see here. So essentially, I'm trying to think of how to explain this one. So if we just focus on this again, another way to look at this would be x plus y. Fine, yeah, x plus y over 2 is equal to t, right? So if I square it, but that's also equal to x minus y over 2, right? So we get this equation, if you will, x minus y is equal to 2 times x plus y. Let me get the, sorry, I'm trying to do something here. X plus y squared divided by 2, I guess, yeah. If you make a substitution and you let v equal to x minus y and you let u equal to x plus y, right? And then you make a graph which puts those in there. Like what would v equals to 0 be? V equals to 0 should be like the u-axis, right? V equals to 0 is x equals to y, right? X equals to y is v equals to 0, so that makes this the u-axis actually. And then the other one, this guy, would be the v-axis. So u it so happens that these are perpendicular if you set them equal to 0. The one gives you the line y equals x, the other one gives you line y equals minus x. So you could think of u and v as being a new rectangular coordinate system, or Cartesian coordinate system I would prefer. And with respect to that Cartesian coordinate system, although I think I probably need to do some normalization, but whatever. I'm just trying to give you a sense of what's going on here. This equation becomes what? It's just what? It's v equals to 1/2 u squared, right? Which is a sideways opening parabola. It's this guy. And so for the problem, which is similar, Josh actually has plugged in points and got that using the tabular method, like my example 1. And that's probably the right way to do it, like on a test or something. I don't know. I mean, what's the chance that you're going to invent new coordinates and see, oh, wait a minute, this is actually a rotated parabola, right? I probably wouldn't have seen this if it wasn't for talking to Josh earlier today about a similar problem, all right? So sometimes you can see it through direct manipulation. Like what's a surefire way to visualize a parametrized curve, a path, is to use software, all right? That's pretty much the best way, all right? Which I'll get to here momentarily. Now one last example. So tomorrow we will dive headlong into the calculus of this. But one other standard example. Standard problem. If you've got a point, say P0, say P1, P2. And I've got another point over here, let's say Q1, Q2. Right? So this is a point Q and this is a point P, right? Suppose I want to parameterize the line segment right? Parametrize PQ, you know? This is the usual high school geometry notation for it, right? So here's how you do it. I'll present it as a vector, if you don't mind. You set R of t equals to, and so I want to make this t equals to 0, and I'm going to make this t equals to 1, just to keep things simple. And so to get p at t equals to 0, I'll put a p here. And then to get a q at t equals to 1, I'll put a tq over here. Now that doesn't quite work, because if you put in time 1, I get p plus q, right? So to get rid of the p, put a parenthesis here, and I subtract p. This formula, which I will box, is a go-to for constructing the parameterization of a line segment. This will give you r of 0 is p, and it will give you r of 1 is p plus q minus p, otherwise known as q. So if you ever want to parameterize a line segment from one point to another, this is a surefire way of doing it without a lot of thinking. Let me unwrap. I know you guys are not comfortable with the vector notation yet. That's okay. You got a whole another semester to work on that, right?
I am taking physics 1 and 2.
People have been playing piano for hundreds of years. What did they ever accomplish? Nothing. Nothing. Math. Math accomplishes things. No, gotta do piano. Fine. You're dead to me. Let's see here now. Okay, that might have been too far. Let's see here. 10. No, it's fine. Piano's important, I guess. Let's see here. I'll get over it. All right. So if this is our P and that's our Q, and my initial and terminal point, then so Q minus P is literally 10, 7 minus 1, 3. And guess how you subtract points? You subtract point-wise, I mean component-wise. That actually gives me 9 and 4. If you want me to tell you the truth, this is the displacement vector from P to Q. So R of t is P, which was 1, 3, plus t times 9, 4, which is equal to 1 plus 9t, comma 3 plus 4t. And let me put it back in the lingo of our current chapter. X equals to 1 plus 9t, y equals to 3 plus 4t. There you go. 0 less than or equal to t less than or equal to 1. That is the parameterization of the line segment. Now, I'd be remiss today if I didn't show you how to do this with technology, which will take me all of about 3 seconds. So, assuming that the projector works, of course. You can use Desmos, right? That's cool. This thing, which will eventually show up, is a little program called Graph. It's free, as in it costs no money. Just costs you some time, but not a lot. I think it's like, I don't know, 5 megabytes or something. It's very, very quaint. What was the thing we looked at earlier? Was it t cosine t? Wasn't it? I believe, yeah.
What are you talking about? The ones-
Example 1, t cosine t, right? And we looked at 0 to 3.14, right? There's a better picture of it. As you can see, it was actually curved. I can zoom in, like so. I could do other things, like instead of looking at it from 0 to 3.14, I could look at it from 0 to 10, see what happens. Hey, wait a minute. I think you know what it was, right? But we could easily do other things, like what happens when you do look at like t times cosine t. Ooh. Well, that's more funky looking. So there's that one. The other thing, of course, I like to use is the Desmos, which is handy, and you can do all kinds of fun stuff. Like we could do like t times cosine t. Well, let's do kt, and t times sine kt. Now, I use a slider k. I would love to put the slider just directly in the domain. It won't let me do that, so instead I put it in the multiplier. So that means is I'm effectively come on. Ah. Whee! There we go. There you go. You can stare at that for a little while. You will pass the final. You will pass the final. Oh, I'm supposed to give you guys back your test, aren't I? Let's see here.
We should try that for a class session. We stare at that while it's
Alexandra? Tamara? Oh, you turn it off?